So based on that variable separable, that is not variable separable method, the elliptic hyperbolic PDE, I am giving one more bit, you later you try it, which is given 2010. That second example, first example I have already done. The linear second order PDE 5 del square 5 by del x square plus 3 del square 5 by del x del y plus 2 del square 5 by del y square plus 9 is equal to 0. Is elliptic B, parabolic C, hyperbolic D, none. Okay, you please check, this answer is elliptic. Next, so in other branch 2013 this is given. Laplace equation for water flow in soils is del square h by del x square plus del square h by del y square plus del square h by del z square is equal to 0. Full stop. Heat H does not vary in y and z directions. Boundary conditions are at x is equal to 0, h is equal to 5 and dh by dx is equal to -1. Full stop. What is the value of h at x is equal to 1.2 question mark. Solution. H does not vary in y and z directions implies del h by del y is equal to del h by del z, both are equal to 0. H is a constant y and z direction. So therefore given equation reduces to what is that? Only del square h by del x square, that is I can write d square h by, because only one variable, d square h by dx square is equal to 0, integrating dh by dx equal to some c1, again integrating h is equal to c1x plus c2. Okay, integrating with respect to x, because only one variable, that's why I didn't write first time integrating with respect to x, only integrating. Or you can write here Okay, so what we will be getting? After integrating, h is equal to constant integration, constant to x, because we are doing with respect to x. Not required to write because only one variable y and z direction is already constant. So let us say this is equation 1 and equation 2. Use the conditions given. X is equal to 0, h is equal to 5, and dh by dx equal to minus 1. That is at given at x equal to 0. So therefore, how much? dh by dx minus 1. C1 is equal to minus 1 and 5 is equal to minus x, that is C1 into x value 0 plus C2 implies C2 is equal to 5. So therefore h is equal to minus x plus 5. What we require? The value of h at x is equal to 1.2. At x is equal to 1.2, comma, h is equal to minus 1.2 plus 5 is equal to 3.8. That is the answer. Next, note. For elliptic PDEs, for boundary conditions are specified for closed regions, whereas for parabolic PDE, two boundary and one initial condition are required. Okay, and for hyperbolic PDE, two boundary and two initial conditions are required. See, This is very, very important. 1 mark question, 2 mark questions, or just refer the partial differential equations. This is heat, one-dimensional wave equation, one-dimensional heat conduction equation, two-dimensional heat conduction equation, steady state Laplace equation. The procedure 60 marks, 8 marks questions. What you have studied in Max 2 paper in BTech. Okay, refer textbooks. Then you identify this: how many boundary conditions, how many initial conditions are required to solve the 3 standard equations, one-dimensional wave equations, its uses in vibrations of stretching, one-dimensional heat equation, two-dimensional heat equation in steady state flow. Okay. Next. Solution of 1D, one-dimensional wave equation. Its use in problems of vibrating string. Dou square y by dou t square is equal to c square dou square y by dou x square. Equation 1 is called 1D wave equation. Okay, subject to the two boundary conditions, two initial conditions, because this is a hyperbolic PDE. Okay, y of 0 t is equal to 0 for all t, y of L comma t is equal to 0 for all t. So this is 2, this is 3. These are boundary conditions. Boundary conditions. And two initial conditions. Y of x comma 0 is equal to some f of x for 0 less than or equal to x less than or equal to L. Dou by dou t of y of x comma 0 is equal to some g of x for 0 less than or equal to x less than or equal to L, where L is the length of the string. This is 4, this is 5 initial conditions. Initial displacement, initial temperature. So this problem tells that the displacement, that is y of x comma t. Okay, y of x comma t is the displacement. Okay, here equation 1 is hyperbolic. If we check that condition, b square minus 4ac greater than 0. Just remember 1, 2, 3, 4, 5, because it is 16 marks, 8 mark question. but you just remember the main what I am giving the condition equation 1, how to find the solution. Okay, by heart this condition. The appropriate solution of equation 1 means given is y of x comma t is equal to a cos px plus b sin px times c cos pct plus d sin pct. Because of 4 conditions we have to determine ABCD constants and P also. Okay, let us say this is 6. Using 2 comma 3 we get A is equal to 0, P is equal to n pi by L. Just these proofs are available in the textbook. Okay, after this the last I mean 6th what I am going to give, now the equation you just by heart the solution, that is therefore the most general solution of equation 1 satisfying 2 and 3 is, this is very important step, y of x comma t is equal to summation n is equal to 1 to infinity Cn cos n pi ct by L plus dn sin n pi ct by L into sin n pi x by L. This is equation 7. And the other 2 conditions left, that is initial conditions, we will get C and Dn using 4 and 5 conditions. Using 4 and 5 comma we get Cn is equal to, using Fourier series, this is integral 0 to L f of x sin n pi x by L dx, and dn is equal to 2 by n pi c integral 0 to L g of x sin n pi x by L dx. Remember C and dn and equation 7, that is sufficient, and equation 6 and the given partial differential equation. You just by heart, that is for 2 marks, 1 marks. Proofs are available, all these up 10 in the textbook. You just refer the standard textbooks. Here n is equal to 1, 2, 3, so on. Just the most appropriate solution and most general solution first of all, and a value, p value, that is C and dn values only. Okay, along with given differential equation. Solution of one-dimensional heat conduction equation. Also this is diffusion equation. to determine the temperature in one dimension. Okay, the equation dou u by dou t is equal to c square dou square u by dou x square, equation 1, is called 1D heat equation. It's used to determine the temperature, okay, at any time t, subject to u of 0t is equal to 0 for all t, equation 2. U of L comma T, where L is the length of the rod, boundary conditions, that is the temperature at the end points has no change. That means the temperature keep the temperature at the end points of the rod or bar of length L is equal to 0. Boundary conditions and initial temperature. U of x comma 0 is equal to sum f of x throughout the rod for all 0 less than or equal to x less than or equal to L, equation 4. This is initial temperature of the rod. By heart, equation 1. Conditions given available in the problem only. Equation 1 and solution and most general solution for every topic. The appropriate solution of equation 1 is u of x comma t, temperature in the rod, is equal to a cos px plus b sin px multiplied by e power minus p square c square t, equation 5. The most, just like as above, a0 p is equal to n by pi, well, using 2 and 3. General solution of equation 1 satisfying conditions 2 and 3 is y of x comma t is equal to sigma n is equal to 1 to infinity bn sin n pi x by L e power minus n square pi square c square by L square into t. Very, very important. This is equation 6. Just remember 5 and 6. Solution and most general solution satisfying the two conditions. Okay. So what is the condition left here? To use fourth condition. Using condition 4, we get this Bn value is equal to 2 by L half range sine series. That is, this topics Bn, An, C and Dn, all values came by Fourier series only. 0 to L f of x sin n pi x by L dx. But proofs are not required, just remember the values where I am putting the ticks. Okay, and this is also equation, not the conditions, not required to, but you remember how many conditions are required? 3 conditions, 4 conditions, which I already given by note point. Okay. The next one is depending on the options you that is what you remember the each case, general solution, most general solution, okay, then Cn Dn in the previous topic, here Bn value. Solutions of Laplace's equation, which we already solved in 3D, one problem. Laplace's equation. Its use in problems of two-dimensional, that is 2D, steady state heat flow. Steady state heat flow. Steady state means that u, whatever the variable dependent variable is independent of time. Dou u by dou t, dou x by dou t, all these are becomes 0. Okay. And the previous problem, it's used in problems of one-dimensional unsteady state heat flow. The previous one is 1D heat equation, unsteady state heat flow, that is dou u by dou t is there, del u by del t, that is dependent of time. In this, independent of time, steady state flow. Okay. Previous one is, it's used in problems of one-dimensional unsteady state heat flow. I forgot to write there. The equation dou square u by dou x square, del square u by del x square, del square u by del y square is equal to 0. In some textbook, this LHS is denoted by del square operator, Laplacian operator. That's why this is called Laplacian equation. Equation 1 is called Laplace's equation in 2D. 3D, del square u by del z square, independent of time t. Okay. The various possible solution of equation 1 are, first I am writing here, u of x comma y is equal to a1 e power px plus b1 e power minus px times c1 cos py plus d1 sin py, equation 1. And u of xy is equal to a1 cos px plus b1 sin px multiplied by c1 e power py plus d1 e power minus py. Say solution 2. Depending on the nature, we have to take appropriate solution. The third one is u of xy is equal to a1x plus b1 c1y plus d1. a1x plus b1, or just for understanding, second solution, each suffix denoted by 2. Better to denote a2, b2, c2, d2. First solution, first suffix all ones, all suffix 2 indicates second solution, suffix 3 indicates third solution. Equation 3, c3 d3. Okay. Depending on the options only, you take the solution. Of these, comma, we take that solution which is consistent with the given boundary, with the given consistent here boundary conditions. Okay. So of these three solutions, we have to take the solution which is consistent with the boundary conditions, given boundary conditions of the problem. Okay. But sometimes the one of the options, that is the question asks what is the solution of the Laplace equation. One of the option belongs to like that, 2 marks. You remember, you by heart these three and the previous two, that is sufficient. So now I am going to Laplace equations, Laplace transforms. Next unit is Laplace transforms. Let f of t be defined for t greater than or equal to 0, or depending on other or textbook, t greater than 0. Then the Laplace transform of f of t is defined as L of f of t is equal to, you can use any bracket, curly bracket, square bracket or open bracket, 0 to infinity e power minus st f of t dt is equal to f bar s or capital F of s. Provided that the integral exists. Provided that the integral exists. S is a parameter, maybe real or complex. See, L of f of t, Laplace on f of t is given by integral 0 to infinity e power minus st f of t dt. After integrating and substituting t lower limit, t upper limit, then it gives an s term, function of s, we don't know that value, denoted by f bar s or f of s, capital F function. So to avoid the confusion between capital F and small f, that's why denoted by f bar s. In some textbook denoted by f bar s or capital F of s, provided this integral exists. That integral exists in terms of some s value only, then only this is the definition true. Okay, so this is called unilateral transform. Okay, I can write this is one-sided Laplace transform, unilateral transform. Okay, for bilateral transform, that is minus infinity to infinity e power minus st f of t dt. Okay, now the Laplace exists for some s values, that is the condition regarding s values. The s values corresponding to each function f of t whose Laplace exists are called region of convergence. Okay, ROC. Now, and L inverse f bar s is equal to f of t is called the inverse Laplace transform of f bar s. I mean f bar s. So t is time domain, s is frequency domain. L is an operator changing time domain to frequency domain, and L inverse is an operator change from frequency domain to time domain. Okay. L is called Laplace transform operator, L inverse is called inverse Laplace transform operator. Now I am going to give the formulas for Laplace of some standard function, that is elementary functions. Laplace transform. Now LT stands for full form Laplace transform. Side by side I am giving ILT, inverse Laplace transform. Okay, of standard functions. First one, L of 1 over s if s greater than 0, or you can write later, and L of k is equal to k by s. This k is any constant. Okay, if s greater than 0. L of e power at is equal to 1 over s minus a if s greater than a, and L of e power minus at is equal to 1 over s plus a if s greater than minus a. Okay. L over L of cos at s by s square plus a square, and L of sin at a by s square plus a square if s greater than 0. For the See, if these s values assumed, then only the Laplace of these functions is equal to the corresponding answers. Okay? That s corresponding s values for every formula. Against to every formula, I am giving some s values. That s values are called region of convergence. 4. L of cos hat is equal to s over s square minus a square. Okay? And L of sin hat a over s square minus a square if s greater than mod a. 5. L of t power n is equal to two cases, n factorial over s power n plus 1 if s greater than 0 and n is equal to whole numbers, 0 with natural numbers. Other case, gamma, this symbol capital gamma, n plus 1 divided by s over n plus 1 if n is a fraction but not a negative integer and s greater than 0. So with that s values against to each formula assumed, then only that Laplace exists. The right side answers. Okay. So on this side I am giving 1. LA inverse 1 over s is equal to 1 and LA inverse k over s is equal to k. This is constant. Okay, just write in reverse now. LA inverse 1 over s minus a is equal to e power at and LA inverse 1 over s plus a is equal to e power minus at. 3. LA inverse s by s square plus a square is equal to cos at and LA inverse 1 over s square plus a square. I am not considering a over s square plus a square, but for some problems in inverse, use numerator directly like this, 1 over s square plus a square. Bring that a into the right side, sin at over a. 4. LA inverse s by s square minus a square is equal to cos hat and LA inverse 1 over s square minus a square is equal to sin hat by a. Last one, LA inverse, just I am considering with the other side, 1 over s plus s over 1 over s power n plus 1. Send that constant into other side. So two cases, t power n over n factorial if n is equal to whole number, 0 with natural number. Other case, t power n gamma n plus 1 if n is a fraction. N is a fraction but not a negative integer. Okay, but not negative integer. There is no place. Here I am writing but not negative integer. Just by heart these standard formulas. So now I am giving a note point to derive the gamma for positive integer and negative fraction, positive fraction, because some problems depends on that evaluation of gamma. Note, first point, gamma 1 is equal to 1. And gamma 1 by 2 is equal to root over pi. Just remember, these are two standard gamma values. Okay. Second note point. If n is a positive integer, comma, define gamma n is equal to n minus 1 factorial. Subtract 1 and then apply factorial. See, example, gamma 5 is equal to 5 minus 1, 4 factorial value 24. Okay. 3. If n is a positive fraction, n is a positive fraction, comma, define gamma n is equal to n minus 1 times gamma n minus 1. Subtract 1 from the given number, write that value, obtained value outside as well as inside. See, example, gamma 7 by 2 is equal to, so this is your n, subtract 1, 5 by 2, gamma 5 by 2. So where do you stop this procedure? Until to get a proper fraction. Proper fraction means numerator less than denominator. So this is 5 by 2, 3 by 2, subtract 1, 1 by 2. 1 by 2 is a proper fraction. So whenever you get proper fraction, multiply by its gamma, because n minus 1 into gamma n minus 1. So this simplifies to, later you write, this value is already given, root pi. Okay. This is the way to evaluate, continuously subtracting 1 until to reach proper fraction. Whenever you get proper fraction, multiply by its gamma. Similarly, see, 11 by 3, this is your n. Okay. Subtracting 1 continuously, first one is 8 by 3, next subtracting 1, 5 by 3, next 2 by 3. 2 by 3 is a proper fraction, multiply by its gamma, and we don't know gamma 2 by 3 value. They will provide, or they, in the gamma table books it is available, gamma 2 by 3, but we have to remember this gamma half 1 by 2 proper fraction, but we cannot remember whenever a proper fraction is obtained, its gamma is difficult to remember. Okay, whenever you get to any proper fraction other than this, it is difficult to remember. Okay, not required to by heart. Your options also like that only. If n is a negative fraction, comma, define gamma n is equal to gamma n plus 1 divided by n. Just this formula is obtained in the above by replacing n by n plus 1. Because if you apply the above problem for negative fraction, nowhere it gets a proper fraction. From a negative fraction, if you go on doing subtracting 1, the problem never ends. Okay, you will not get a proper fraction.